Westermayr, who has accepted to give a talk this afternoon. And let me give you a short introduction about Prof Julia. She studied chemistry at the University of Vienna in Austria, where she worked under the supervision of Prof Leticia Gonzalez and Dr. Philippe Marquetin. She got her PhD in 2020, and she was awarded the Uni Docs Fellowship of the university and received the Sigrid P.M. Rimov Prize, which is a PhD prize that is yearly awarded to outstanding PhD in German-speaking countries. After her PhD, she received a fellowship of the Austrian Science Fund for her postdoctoral studies that she carried out with Prof. Reina Mora at the University of Warwick in the UK. Before finishing her postdoc, she already got the junior professor position at the University of Leipzig since October last year. In her research, she used artificial intelligence to develop new methods and theories to better understand light-matter interaction and to leverage this knowledge to accelerate molecular and materials discovery. So, Prof. Julia, it's a pleasure to have you. You may start your talk. I think you'll have 45 minutes and a few more for question later. So thank you.
Perfect. Thanks a lot for the introduction and thank you for inviting me. I'm going to talk about our work on machine learning for excited state molecular dynamics. And I want to start to introduce you to this topic by thinking what would happen if there was no light. And I strongly believe that life would not exist in the way we know it. For instance, photosynthesis, human vision with the eye, or phototherapy all depend on light-induced reactions. But there are also some negative side effects of light-induced reactions, such as skin alteration and skin cancer, bleaching, or blindness. And if we want to understand why these reactions take place in a way they do, it's often inevitable to take a look at the smaller chromophores that can absorb light and give rise to the photochemistry that we are interested in. So if we want to understand what happens after light excitation, so I'm mainly gonna focus on small molecules now, because it's already super difficult to describe excited states on small molecules. But if you want to understand these, then there are several questions we might ask. And the first one is, can the molecule actually absorb light? So if light hits the molecule, can it absorb it? And we can answer these questions with UV-Vis absorption spectra, which you can see here, for example. So you have the excitation energy and then the intensity for every peak. So if we know that the molecule can be excited and can absorb light, we know that it can enter a higher electronic state. Now, the second question that we might ask is, what processes take place after light excitation? And these answers can be found with excited state molecular dynamics. So what we basically do is we follow the motion of the molecule on the excited state potential. And whenever there are transitions between the different states, these can either be ultra fast and radiationless, or they can be radiative. And depending on the type of transition, we can explain whether a molecule is photostable or not. Okay, so there is one very efficient method with which we can study excited state processes. And this is called surface hopping, and I will only talk about surface hopping during this talk. And this method is a mixed quantum classical method for excited state dynamics, where the nuclei of the molecule are treated classically, but they move on the potential energy surfaces that are made up by the electrons and that are described with quantum chemistry. So if we have our molecule here, it is excited to an excited state, and then it can move from one potential to the other. So the hops between these states are determined stochastically, and they are based on the couplings between the potentials. And because it's stochastic and because we want to be as exact as possible, we want to approximate a wave packet. So what we usually do is we do not only excite one molecule, but we sample different conformations, excite all of them, and then we get the different reaction channels that can take place. So the conventional approach is if we study light absorption and photodynamic processes is with quantum chemistry. So if we want to simulate a UV visible absorption spectrum, for instance, then we have our molecule and we need to sample many conformations. So we need to do many thousand calculations in order to get an accurate absorption spectrum. So if we do this with a very accurate method like multi-reference, the simulation would take about 1 day on a CPU. Now, if we do excited state molecular dynamics, then it looks a bit different because here we cannot just do all calculations at the same time, but we need to do them after each other. So we start with a molecular structure. We do a quantum chemical calculation, get a point on a potential energy surface. Then we propagate the nuclei and we get the next time step. And we do this iteratively. So this takes a lot of time. And if we simulate the photodynamics with multi-reference configuration direction, then it would take us about 19 years to simulate 1 nanosecond. And I guess no one wants to wait 19 years to get the nanosecond dynamics of this small molecule here. So our goal was, or the goal during my PhD was to get rid of the quantum chemical calculations and replace them with machine learning. So where can machine learning actually help for excited state simulations? And there are quite a few occasions where we can use machine learning. So for instance, we can start very basic. We can start with the parameters, and this would be, for instance, to learn a density functional or an active space, or we can learn different outputs of a quantum chemical calculation. And the most powerful would be to learn a primary output. This would be, for instance, a molecular wave function. And there was a paper that was just published yesterday by Frank Noé and Jan Herman, and they did electronic excited states in deep variation of Monte Carlo. And so this is their first steps into getting a molecular wave function with machine learning. Most work is actually done on doing machine learning for the secondary outputs. This would be learning the potential energy surfaces or the couplings. Then we could also use tertiary outputs. This would be learning the UV spectra directly, for instance, or the dynamic outcomes. Or we could also use machine learning to analyze the data in the end. And what I'm mainly focused on today is to learn the secondary outputs, because we can use the secondary outputs to predict the tertiary outputs. And this is what we implemented in the Schnack code. So I'm going to show you now what we did on machine learning for excited states on the simple test case of the methylene ammonium cation. So I'm very sorry for all the material scientists, but now I'm going to focus on small molecules only. So if we want to simulate UV absorption spectra and photodynamics, what do we actually need? So if we look at this spectrum here, then what we need are the energies, and we need the transition dipole moments, because they give rise to the intensity of a peak. So in order to compute the intensity, also known as the oscillator strength, we need the energy gap between the potentials and the square transition dipole moment. An alternative would be, of course, to learn the intensity directly, then we don't need the transition dipole moment. So for photodynamics, the process looks a bit more complicated. So if we start here, then the molecule gets absorbed. We need the energies, which are the potentials here, and the forces to move the molecule along. And when we enter a region like here, which is called a conical intersection, there can be transitions from one state to another. And transitions of the same type are called conical intersection, and the transitions are internal conversion. And we need nonadiabatic couplings for this. But we also have states of different multiplicity. For instance, in red, we have triplet states. And if a triplet and a singlet cross, we have an intersystem crossing. And for this, to describe these transitions, we need spin orbit couplings. So what we need are energies, forces, and the couplings between the potentials. The model that we used to do machine learning for this was a neural network. And what we wanted to do is we wanted to find a relation between an input, the molecular geometry, and the output. And as mentioned, the output are the energies of the electronic states, and then the coupling values and the transition dipole moment. So there are different steps that we need to take in order to get to the machine learning model for excited states. This is, we need an input. So we need to translate the molecular geometry to a descriptor that can be learned by machine learning. We need a training set, and then we somehow need to represent the output in an accurate way. And I'm going to start with the input. So there are different ways to represent a molecule. If we just look at the methylene-ammonium cation here, then we could use the simplest descriptor. This is actually also what we did in the beginning. And this is the inverse distance matrix, which is basically 1 divided by the distances between the atoms. But if we want to use the same machine learning model for another molecule like ethylene, where here the nitrogen is a carbon atom, and we have exactly the same geometry, then the model would not be able to distinguish these systems. And then we could, for instance, use the Coulomb matrix, which adds the elemental charges here. But these descriptors still have problems because they are limited to systems that have the same number of atoms. And they are also not permutationally invariant, which means that if you swap the lines in your XYZ file, this would fail. So how to describe molecules of different sizes, like how to describe many molecules in one model. And for this, we would need atom-wise descriptors. So the simplest way is to use a molecule-wise descriptor as the inverse distance matrix that I showed before. But if you want to describe more systems, then we need atom-wise descriptors. And these look at molecules atom-wise. So we have here an atom, the hydrogen atom. We have a cutoff region. And the model only models this hydrogen atom in the atomic and chemical and structural environment. So we get the energy of this atom. Then we look at the next atom and we model the atom in its environment again, and we get an atomic energy contribution. And we do this for every atom, and then we sum up all the energy contributions to get the total energy. And this has the advantage that we can use different molecules and molecules in principle of any size. So this would also be more suitable for different materials. So we have chosen the Dashnet descriptor, which is a message passing neural network, which learns the molecular representation. So what it does, you only have to give an XYZ file to Schnack, and then it, based on the elemental charges and distances, it generates a descriptor. So it actually learns the descriptor, and then it also learns the relation between the descriptor and the energy. Now, how does this work? So if we look at the methylene-ammonium cation again, we start with an embedding layer. So we look, for instance, at A and B, and we embed these two atoms with just two feature values. Then these enter the first layer. Then we have these embeddings here, and then we add the distances. So if we look at A, we add the distance from A to B because it's the direct neighbor. So we add this value here. If we look at B, then we have the neighbor A, C, and D. So the next feature would be a bit larger because we take into consideration all the neighboring distances. So we get our next interaction layer, and this then enters again the next interaction layer. Again, we enter the distances between all the neighbors, and by doing so, we get the effects beyond distances. So somehow we get many body interactions. So this is the input that we have chosen, and we implemented this. So this is basically done. And now let's look at the training set. So in order to actually learn the relation between an input and an output, we need some data. And there are different ways to generate a training set. And first, you need to choose a reference method because the methylene-ammonium cation is so small. We could use a very accurate method, a multi-reference method, and we wanted to describe 3 singlet states. Now, the goal for the training set is because quantum chemistry is kind of expensive, especially if you want to go to larger systems, we want that the training set contains as few data points as possible. But the training set should also be complete. But this is very problematic, especially for photodynamics, because we do not know what will happen in the beginning, but we need to describe all of the processes that might take place. And if we have a too small training set, then the machine learning force field will probably explode, as you might know it from molecular mechanics when you don't have a good parameterization. So the way that we then developed the training set was with the adaptive sampling approach that was developed by Jörg Behler for the molecular ground state, and we adapted it. So we started with some initial data that we generated randomly, for instance, by changing the bond angles and the bond lengths. And then importantly, we trained at least 2 neural networks. And then we did molecular dynamics with both of these models. And at every time step, we compared the predictions of these 2 models. And at some point, the models might start to deviate from each other. And we can detect these data points. And then if we detect such a data point, we can do a reference quantum chemical calculation. And in this way, we could build the space that is needed for the dynamics on the fly. So in principle, the more data we should add, the better the machine learning model should get. But when we did this, this was not the case. And in fact, the models started to get worse. And it took us quite some time to find out why this was the case. And the reason was the arbitrary phase of the wave function. So you probably know that the wave function is not uniquely defined because it carries an arbitrary sign of +1 or -1. And I want to explain this to you by taking a look at molecular orbitals. So if we have just one state, S1 here, then we have an input geometry, and we predict a molecular orbital. For instance, it's red. Now we can assign a red orbital a sign of +1. Now if you look at another state, then we get another orbital, and we can also assign this orbital +1. Now, if we compute a property between 2 states, such as the transition dipole moment or the nonadiabatic coupling, then the state of these 2 different, the sign of these 2 different states enters. So we have +1, +1, we get a positive sign of the coupling value. Now, if we do this again, it might be that one orbital switches. So we get here a negative sign, we still have a positive sign, and then the sign of the coupling value switches. And this is arbitrary. And if you do this along a reaction coordinate, you get signs that arbitrarily switch. And this is very problematic for machine learning because they are smooth by definition, and these are not smooth functions. So what we had to do was we had to choose a reference geometry, which was the equilibrium structure, and we fixed the phases, and then we computed the phase change to every other data point in the training set, and we corrected the phases with respect to this one. And in this way, we could generate smooth coupling values. So we called this the phase correction algorithm, with which we could get smooth couplings. And by correcting the data points, we could retrain the models. And we generated the data in this way. And with this, we got the final training set. So now that we have the training set, we still need to find out how to actually represent the energies, the forces, and the other properties. So as already mentioned, we need energies, forces, couplings, and dipole moments. Now, there are a few questions that we had to answer. And the first one was, how many models do we actually need? Like, we could describe all properties in one model, or we could use separate models for each property. So what we found was that treating properties that are similar to each other, like energies and forces, in one model is beneficial, while treating couplings and dipole moments in one model is not very good. And the other question was, since we are not only dealing with one potential energy surface, but with many, how many models should we use for that? So should we treat every excited state in a separate model or all together? And in a collaboration with Anatole von Lilienfeld, we found that it's better to treat all excited states in one model. And this is what we call multi-state networks. So let's go to the energies and forces. Is there a question? Which descriptors? May I answer the question that was asked which descriptors I'm using for the machine learning. Yeah, so the descriptor that we use was Schnack. Schnack automatically learns the descriptor. I hope that this answered the question. Yeah, okay, so and then the descriptor goes into automatically is passed into the next layer of Schnack, and then it's mapped to the energy. So we describe all states in one network. And if we just look at the energy, it's a scalar property. So if we have this molecule, we get this energy value. Now, if we rotate the molecule, which is somehow not shown, then the energy is still the same. But now if you look at vectorial properties like the forces, and then we rotate the molecule, then the force vector changes the direction. So
sorry, I think there is a question from Ralph.
Yes.
Okay, now I'm unmute. I didn't manage to unmute myself. Sorry.
Okay.
Yeah, sorry for interrupting. So there's one thing which I don't understand. So you explained to us that while you're looking for the description of the molecule at every atom, and then there's kind of a cutoff radius beyond which you kind of do not see the environment. Okay, so now let's imagine obviously a bigger molecule than this very small one. Okay, so however, for excited states, I mean, even the density of states you will have might depend very much on how big your system is. I mean, you see, with a small molecule like here, you will have, I don't know, 3, 4 states in a given energy range. If you add some ligands or some other things, many new states will appear there. So what is not clear to me in your approach is how, on one hand, this cutoff radius beyond which you do not see anything goes along with the fact that far away atoms and ligands can lead to the appearance of states. You know what I mean?
Yeah, that's a very good question. So one advantage of message passing networks is that you can somehow go beyond the cutoff by adding the distances and the functions again and again. So you somehow see beyond the cutoff, but not too far. So there are currently developments on equivariant descriptors that are less local than these descriptors. But still, for excited states compared to ground state, you need much larger cutoffs. So we usually use 10 to 20 angstroms, which is a lot. And so in
this case, you have your whole molecule always within the range.
Yes, somehow.
Okay.
Somehow, yes. And what people, there are not really a lot of works on excited states for really, really large system and materials. But in this case, I might go to local potentials and somehow describing the non-local interactions in an additive fashion externally or in a non-global network.
I see.
And separating locality and non-local.
Yeah, I mean, the question why I'm asking this is that for ground state things, one of the forces of these machine learning things is that one can learn or train your system on small systems, and then only in the machine learning stage one goes to the larger ones. While for excited states, I always see this basic problem that if you go larger, you get a larger density of states, and this somehow must be there.
Yes.
Yeah, okay, but
yeah, that's a really tricky question. I totally agree.
Sorry
there
for
are a lot of
interruption.
things that we still need to do in this direction. No, thanks for your question. Okay, so yeah, when we want to describe, then we had scalar values, which we can describe in a normal network. But if we want to describe something like the forces, then the vector changes when the model rotates. So what is basically done is we take the derivative of the energy to describe the forces, and in this way one can build covariance via the derivatives into the network, and additionally during dynamic simulations the energy is automatically conserved. So when we look at non-adiabatic coupling vectors, there are different problems. So first, why do we need them? So if we move along a potential and then we enter a region a critical region, like a conical intersection, the question is, where do we move? Do we move up or do we move down? And this is actually dependent on the coupling strength between these potentials. Now, the non-adiabatic coupling vectors are inverse proportional to the energy gap, which means that here, when two states are degenerated at the conical intersection, the coupling vector is singular, and this is extremely problematic for neural networks. So what we did with Professor Anatola von Lilienfeld is we trained interstate couplings, so we trained smooth couplings. We multiplied these with the energy gap, so we got this curve here. And for the prediction, we predicted the smooth couplings and divided it by the energy gap. Now, the couplings are also vectorial properties. So we did exactly the same trick as we did for the energy. So we predicted the couplings as the derivative of something. And this something was just a latent property the neural network has never seen. And this something is also the antiderivative of the non-adiabatic couplings. I see another question. So at the excited state of a molecule, all atoms of that molecule have the same energy. So every excited state has a different energy, and also the atomic contributions cannot really be computed. So the neural network just predicts atomic contributions for every atom, for every excited state, but they do not necessarily have to be the same energy for every atom. It strongly depends on the environment and the atom type. But they don't have to make sense, the atomic contributions. It's just a way to get to the total energy. I hope.
Yeah, sorry, Julia, but if you take the atoms to infinity, does the neural network predict the correct excitation for each atom?
Yeah.
Okay, it does. Okay.
Yeah, so we predict atomic energies and then we sum them out.
Yeah, but what I'm asking is, if you separate the atoms, take the atoms to infinity, then the neural network still predicts the excitation for each atom, does it?
Yes, somehow.
Okay. Yeah,
but
that's fine. Yeah.
But we don't look at the atomic energies, but only of the whole system.
Yeah, I understand. Yeah, thanks.
Okay, you're welcome. Okay, so we use a trick to learn the couplings by predicting a random value and then doing the derivative of this. And the same trick we use is when we describe dipole moment vectors. So as already mentioned, we can either learn the oscillator strength directly, which is a scalar value, so we do not need to consider any additional network architecture. But when we learn the dipole moments, these are vectorial properties. And again, for instance, if we have a vector here, the dipole moment, and for some reason it doesn't rotate. Yeah, but if it rotates, if it would rotate now, then the vector would change. So what we do is we describe the dipole moment by taking the charge model, which was developed by Michael Gast-Ecker for neural networks. So the loss function, what we learn are the dipole moments, but the neural network predicts us here atomic partial charges. So we predict partial charges for every atom in our system, and we do not have the reference data for these, but we know that we can multiply these atomic partial charges with the radius of each atom to the center of mass. And by summing this up, we get the dipole moment. And we then learn how good this physical relation is represented with the neural network. So now we have our input, we have the training set, we have the output. Now we can go to the application. And first we wanted to see whether our machine learning model actually works for photodynamics. So we wanted to reproduce the excited state dynamics of quantum chemistry. So we simulated dynamics for 100 femtoseconds, and you can see the results here. Continuous lines are machine learning, dashed lines are quantum chemistry. And you can see that at time 0, the molecule is excited to the second excited state. And then there are ultra-fast transitions to the first excited state and then back to the ground state. And you can see that the population curves match very well. So we were happy with it and thought, okay, it works. Now, because machine learning is much cheaper, we could simulate thousands of trajectories and get smoother population curves and better statistics. Now, why is this important? Imagine you have a rare event. This happens in 1 in 1,000 cases. Now, if you can only do 100 trajectories and sample 100 conformations, you're likely missing this rare event. But if you can simulate thousands and you do active learning and add data on the fly, then the neural network can capture these events. And finally, we wanted to know whether we can go with the approach beyond what is possible with quantum chemistry. So we wanted to simulate the dynamics for 1 nanosecond. You can see that the population stays in the ground state. And but this was kind of a proof of concept that we can go beyond what is possible with quantum chemistry, and we achieved the simulation in about 60 days, so 2 months, whereas quantum chemistry would have taken us about 19 years, and this was done on a single CPU. So we could do photodynamics. Now we wanted to see whether we can also use the approach to predict spectra. So we did Wigner sampling of the methylene ammonium cation, and then we predicted the energy gaps between the ground and the first and the ground and the second excited state. And you can see here the reference absorption spectrum, and here the one that we predicted with Schnack. And you can see that they match quite well. Now, the reference calculations took about 1 day or 17 hours for 500 calculations. And with Schnack, it took about 10 seconds to get the 500 calculations, but the training took about 11 hours on a GPU. And the nice thing about this approach now is because we have our charge model, we are actually predicting not the dipole moments, but we're predicting the atomic pi share charges. So we can also get the electrostatic potential for free. And we can get it at the accuracy of the reference method. So now we have the accuracy of the electrostatic potential at the multi-reference level of theory. And we compared here to the Hirschfeld atomic electrostatic potential. And you can see that it's matches quite well, and for Hirschfeld is not the most accurate approach. Now, the nice thing here is also that we can also look at the charge distribution and the electrostatic potential for the excited states, which you can see here. So in blue, you can see the positive charge, in red, the negative charge, and you can see that the negative charge is somehow shifted towards the nitrogen atom. And yeah, here you can see again the Hirschfeld charges for the ground state. Now, we also wanted to see whether we can now use this approach to train not only on the methylene ammonium cation, but also on ethylene. So we added some data points. So we took the training set, just replaced the nitrogen atom with carbon, recomputed it, and trained also on ethylene. And then we predicted the spectra for both of these systems. And you can see here the reference and the predicted spectra, and you can see that they matched quite well. And so now the model knows how to change what happens if the nitrogen changes to a carbon. I will now answer a question. Do you want to unmute yourself, or should I read it?
Yes, so my question is more like, from what I'm seeing up to now, is that you try to validate your model against reference data that are obtained at the high level of electronic structure. What I'm wondering is, when will you be sufficiently confident on your method where you will not need to do reference? What I'm trying to ask is whether there is a way of going towards the machine learning construction of the surface and be sure that we know that these results are probably as accurate as ab initio calculation without having to cross-check it with previous data.
That's a good point. So one way would be to sample the configurations that you need. Like in the case of Spectra, for instance, you can sample thousands of configurations, and then you can train lots of neural networks on the same data with different random initialization. And then you can compare the models for every prediction. And then if they are similar, you know that you are accurate. If they are not similar, you know that you're not accurate, and that you might need to recompute this data point. And if the neural networks agree for every data point, you are basically fine. And the same is what we do with photodynamics. We always compare the predictions of the energies with 2 neural networks at least.
Okay, thank you.
Welcome. Okay, but here we had the proof of concept, so we wanted to compare and we needed to prove that it works and that it gives reasonable results. So now that the network can learn 2 different molecules, we wanted to see whether we can transfer knowledge somehow. So we predicted the isoelectronic molecules where a hydrogen atom is missing here. You can see here's the reference, here's the Schnack prediction. And it matches quite well, so it's qualitatively okay. And you can see that the first peak is has a lower intensity than the second one, and the energy range is also okay. And here we are between 3 and about 8 eV, whereas before we have been at much higher energies. And we also removed the hydrogen atom here to get the isoelectronic molecule, and you can see that it's also qualitatively correct predicted. So at least for very similar molecule, there is somehow transferability between excited states. So we then implemented all of these developments, and so we combined the Schnack molecular dynamics program with the Dashnet neural network, and we called this then Schnack. So Schnack is freely available on GitHub. And there's also a tutorial if you're interested. And yeah, so we have also added some adaptations. So for instance, you do not need to compute and learn nonadiabatic couplings. You can also predict them from Hessians by using gradient different vectors and second derivatives. Then we also added a faceless loss function. We have a faster GPU implementation, and we have the learning of dipole moments. And here's again how it looked like. So we have, if we do dynamics for 1 nanosecond with multi-reference with quantum chemistry, it takes about 19 years, 100 femtosecond, 70 hours. If we do the old implementation, it took 8 minutes or 2 months. And now the new implementation takes about 24 seconds or 3 days for 1 nanosecond. So I briefly want to mention the faceless loss that we implemented. So as mentioned, we do not really know whether we have twice.
Sorry,
yes.
Can I ask? Okay. What you present is like you avoid the sampling of the vibrational ground state of the molecule that is required by the mixed classical dynamics, and you apply machine learning method. Can this method like simulate the full process, like first the ionization and then the coupled electronuclear dynamics?
I'm not sure if I understood the question.
Yeah, I am asking if the Schnack can describe the full process, first the ionization and then the coupled electronuclear dynamics in the molecule.
So the photodynamics are just coupled electron nuclear dynamics and no ionization.
So this means that you need another method to compute, for instance, but I can see you present the computation of dipole transition matrix that is needed first to compute, for instance, the cross section.
So you can actually use it for both. So you can do the absorption spectra to know to which state you're excited, and then you can do the dynamics. But yeah, so in principle, you can use it for both.
So do you have like this, like it is coupled in the code? Like for instance, if I want to describe, for instance, a pump probe experiment, like can I do it fully in the Schnack, or I need to use another code to compute?
And no, you can use the code, and there is a tutorial on GitHub for both. You just need to train separate models. So you train a separate one for the dipole moments and a separate one for energies, forces, and couplings.
Okay.
Okay. Yeah, and so the good thing is about the new implementation that we have a faceless loss function, which means that we do not need to correct all the data of the couplings and the transition dipole moments. So as mentioned, we do not know whether we have twice a positive sign or negative and positive. So what we do is we compute the error twice. We just assume that once the prediction is correct, and then once we assume that we have a sign change, so we just compute the error between the prediction and the quantum chemistry by switching the sign here. And what we do is we give both of this information to the neural network, and then we can take the minimum function and just take the error that is smallest. And in this way, we somehow can learn data that is inconsistent, because the neural network always takes the smaller error. And if you have more states, then what we do is we take the minimum function of all possible phase combinations. And just very briefly, if you look at this block here, we have the machine learning predictor of the quantum chemistry reference, and then we multiply it with two phase vectors. And these are vectors that contain all possible phase combinations for every state. And the number of possible phases is 2 to the power of number of states minus 1. So this approach can get quite expensive, but at least you do not need to correct all your data points anymore. So here I show you the dynamics that we obtained when we trained on non-phase corrected quantum chemical data with Schnack. And then we just learned using a normal loss function. You can see that the population curves do not match. And when we did phase corrected data, then we get to the results I showed you before. Now, if we use the faceless loss and we take raw data or phase corrected data, in both cases, you can see that the population curves match quite well again. So we get the transitions correctly. Okay, now that we have this implementation, I want to show you what we used it for, and we used it for describing the photodynamics of the amino acid tyrosine.
No.
Okay. So why should we actually be interested in tyrosine? Well, tyrosine is one of the amino acids that can absorb light and gives rise to the photochemistry of peptides and proteins. And the proton-coupled electron transfer plays a role in photosynthesis, but photodamage can also lead to skin alteration, blindness, or drag alteration. And there was experimental evidence that after light excitation, this hydrogen atom here starts to dissociate. And experimentalists suggested a size dependency, which means that if you only look at a small chromophores, there is mainly hydrogen dissociation. But if you look at a large system, then there is also carbon-carbon bond cleavage and other processes. But because the system is so large, many studies only focused on the smaller chromophores, sort of theoretical studies. And we wanted to know what are the differences in the dynamics of the chromophores and of tyrosine. So the first step that we had to do in order to do the machine learning study was to generate the training set. And the experiment was conducted in the gas phase, so we could describe tyrosine in the gas phase, and it was an excitation at 200 nanometers. Then we looked at the experimental absorption spectrum and compared it to a theoretical spectrum, and you can see that an excitation at around 200 nanometers is excitation of the fourth singlet state. So we knew that we needed 4 excited states and the ground state, so we needed to describe 5 singlet states. There was also experimental evidence for phosphorescence, which means that we also need to include triplet states. So in total, we also had to include 8 triplet states that were below the energy of the 5 singlets. So in total, we had 13 adiabatic states. And because we had triplets, we also needed to describe spin-orbit couplings, in addition to non-adiabatic couplings. Now, when we wanted to see which reference method we need, we first took a look at the multi-reference method, because we want to describe the dissociation of a hydrogen atom. So we wanted to describe the breaking and the formation of bonds. But multi-reference methods need the selection of active orbitals and active electrons that are present during your dynamics. And when we computed the reaction path of hydrogen dissociation with different methods, we found here in blue the singlets and in red the triplets, that the potential energy surfaces are not smooth because we have changes in the active orbitals that are relevant during this path here. And we also had intruder states. Now with CASPD2, it got a bit better than CASCCF, but in general, it was, especially because the states were so close, it was not really possible to learn these potentials. Now we took a look at the single reference method, ADC2, very similar to TDDFT, and we found that the potential energy surfaces were smooth, but here at large interatomic distances, the singlets and the triplet states start to split, but this should not be the case, because imagine we have the oxygen and we have the hydrogen, one spin up, one spin down, and now they move apart. At some point, it should not matter whether we have spin up and spin down. So the singlets and the triplets should be degenerate, but they are not. So this is just physically not correct. So what we were left with was, we had a machine learning setup that worked, that we developed for some years, and now we didn't know where to get the potential because no method that we checked could sample the whole phase space that was relevant for the dynamics of tyrosine. So what we came up with was just take the do methods, like take ADC2 and use the smooth potentials where they are correct, and then switch to a method that can describe bond breaking information and add both of these data points to a neural network. So we adjusted the potentials such that they matched each other, and then we fed the neural network with all of this data. And the data curation was quite tedious, and I was very lucky that I got help from 3 master internships in Vienna, and we generated around 17,000 data points. And then we did the dynamics. And here I show you the results. So after photoexcitation, the hydrogen atom here starts to dissociate. But at some point, it suddenly starts to move around the molecule. And when I showed this to my PhD supervisor back then, he told me that this looked completely unphysical and that this is very unlikely that it happens. But the energetics looked fine and the neural networks looked fine. So we searched in literature, and what we found was a paper published in Science, which talks about a roaming atom that was first discovered in formaldehyde decomposition. So we were quite excited, and we wanted to know whether we found roaming, and we validated then this roaming trajectory, and we found that it was really the energetically favored path compared to direct dissociation.
Sorry, Julia, if I interrupt.
Yes.
Was this finding which you found in the literature experimental or theoretical?
Theoretically, back then.
Oh, okay.
The first experiment on roaming was conducted, I think, in 2021, so
okay.
super late.
Yeah, sorry. Mm-hmm.
But now there are more studies coming out that roaming is possibly in more systems and also of oxygen atoms or something like this.
Sorry, a question. So why do you use multi-reference CISD? And why CISD? Apparently the intensity in CISD do not satisfy the sum rule, and it's not sure whether multi-reference CISD.
So here we used ADC2?
Yes,
And,
but
yeah.
no, in previous work you mentioned MR-CISD.
Yeah, it was just as a test system. We looked in the literature because the methylene ammonium cation was simulated quite a lot. And most people used MR-CISD and compared it to other methods, and they found that it was good. And it was a very accurate method to simulate possible bond breaking information.
Okay, so some other question. Have you tried to use machine learning to fit some of the properties and not one, and then try to verify later whether it was still able to describe that additional property well? For instance, you fit everything but the coupling constant, and later you can recover that the machine learning actually reproduced the coupling constant to satisfactory accuracy.
Can you repeat the question, please?
Yeah, I'm asking whether you try to use, for instance, the machine learning to fit all the properties but one or a few of them, and then later check whether the model that you're able to describe can still recover that specific set of properties with satisfactory accuracy.
So yeah, we checked on predicting many properties, but it was the accuracy was worse than learning properties separately. Okay. Except there is a case when properties are somehow connected. So with the coupling vectors, when you multiply them with the energy gap, they are somehow connected. So this works to train them together. But with
Okay.
spin-orbit couplings or dipoles, it was a very bad accuracy.
Okay, thanks.
Welcome. Here, so I think I'm
Sorry,
somewhere.
I just want to fix my idea. Sorry, in this dynamics, the nuclei is still classical, right?
Yes.
Okay, thank you.
Welcome. Here, so very briefly, because we're running out of time. We
Hello.
wanted to see. Beautiful question.
Hello, my name is Steven Nyaranga. My question is, where do you get the data to use in your
For
model?
tyrosine?
Yeah,
So we did active learning. So we started with Wigner sampling and random sampling of reaction coordinates. For instance, we knew that hydrogen dissociation was important, so we added this data from the beginning. Then we trained more, I think 6 neural networks in the beginning, and then we did surface hopping dynamics, and we did the active learning. So when the neural networks diverged, then we added data points to the training set. And for the dissociation, we took some ad hoc generated data with Caspity-2, and then we switched the potentials so that they matched each other.
Oh, so the thing is you generate the data by yourself. Like we don't
Yes.
have a site where you download the data and then you go and analyze.
Unfortunately, we had to generate it ourselves, and it was the biggest part of the study.
Okay, congratulations.
Yeah, so yeah, we wanted to know if roaming has an impact, so we used unsupervised learning, just very briefly, compared to supervised learning, where we know what we want to learn, a relationship, for instance, between a structure and a potential. Now we don't really know what to expect, and it's just like giving the data to an unsupervised learning model, and it hopefully can give us some clusters or results. So we used clustering techniques and separated roaming and non-roaming trajectories. And what we found was that in non-roaming trajectories, there are less hydrogen dissociation and fragmentation, whereas in roaming, we found much more dissociation and fragmentation. And here are some products that we found after our simulations, like p-phenylmethol, which we could also see in the mass spectrum that was recorded at the University of Warwick 10 years ago. But what we only found in roamings were very small fragments, which can also be seen here in the spectrum. And we concluded that roaming can then lead to photo damage. So we also compared the kinetics, which I will skip now. And finally, we also got the question whether roaming atoms are radicals or cations. So we also trained on the dipole moments and predicted the charges for the hydrogen atom, for the roaming atom, for the active state. And we could, in this way, analyze that roaming atoms were radicals. So they are highly reactive species that can actually lead to photo damage. And with this, I come to the conclusion. I hope that I could show you that machine learning is very powerful to complement experiments and give new insights. And there are still a lot of open questions, especially regarding roaming. So is this really a new energy pathway that can happen also in larger systems? What is the influence of an environment? And does this finding influence somehow how we study peptides and proteins in the future? And yeah, if you're interested on machine learning for excited states, we published a review, the tyrosine study you can find here. And Schnack is freely available on GitHub. And there is a tutorial, a Jupyter notebook that starts with this name here. And I'm happy to answer any further questions that you might have.
Okay, thank you. I think if there are more questions, feel free to ask. But right now, okay, I'll probably, there are 3 people who raised their hands. So yeah, if Uriel can start, after it would be Adi.
Sure. Thanks a lot for the talk. It was very, very interesting. So I have a question regarding the long time scale simulation that you do with your method. So basically, I don't understand very well, how do you validate? So how do you know that that nanosecond scale dynamics is okay? Which is the observable that you see to check? Yeah, I mean, so there has been a lot of discussion in the literature about this for example, regarding the effect of so you are doing semi-classical dynamics or the nuclear classical. So there has been a lot of discussion in the literature saying that not including the 0-point energy corrections or something like that, it would generate in the long time scale would generate the problem. So what's your thought about it?
Yeah, that's a very good question. So, I mean, with the machine learning part, we always compared the prediction of more neural networks, and when they diverged, we knew it was not accurate. With respect to quantum chemistry now, yeah, I agree. The 0-point energy correction should be considered, especially for long dynamics. And now, since we can't go to such long dynamics, we might also need to think about, are we really using the correct methods here? So I definitely agree. And I think Mario Babatti did a lot of work also in this direction and on nanosecond simulations of other molecules. It seems to be accurate for nanoseconds. For larger timescales, I'm not sure.
So just to be clear, it was not a criticism. It was just, I just wanted to know your thought.
Yes,
Please, Nicola, can you go on?
Well, I think Ralph was first.
But I had already asked questions. So
okay, well, my question is actually related to the previous question by Ralph. So to the short-sightedness, right? The fact that the descriptors are short-sighted does not mean that there is no, I mean, that you don't see the further atoms, right? Because then you mix these variables in the network. So it depends also on the structure of the neural network, right?
Yeah.
Okay.
Yes, exactly. So the message passing has the advantage that because you pass so often throughout the network that you somehow see a larger environment.
But then you said some people are working on less short-sighted descriptors.
Yeah.
Are they really needed, or do they think they can be more efficient?
They are both. So these are equivariant networks. For instance, Payne or Nequit from Simon Patzner from Harvard and Boris Bushinsky, or Christoph Schütt developed Payne, the equivariant net version. And they give much lower accuracy also for larger systems. And they evaluated it also for some properties that are especially affected by long range effects. And they could use shorter cutoffs than they could use when they just used Schnack and the normal architecture.
Okay, thank you.
Ralph or Ali, whoever wants to go first.
Yeah, okay, so let me ask a question. So what I didn't, so very nice talk, thank you very much overall, but one thing was not clear to me at all. At a certain point, you changed a nitrogen atom with a carbon atom, you obtained ethylene, and then you said you used the same network, and suddenly you also got good results. How is this possible? How, without relearning, how can your neural network know what carbon and nitrogen, what happens? I mean, why didn't you have to learn everything again?
Okay, sorry, I think I didn't really explain this properly. So what we did was we took the methylene ammonium cation training set. We took the structure because we didn't want to sample the structures with active learning again. So in our input file, we just replaced the nitrogen with carbon, and then we did quantum chemical calculation for ethylene.
Ah, so you had the data for the ethylene. Okay. Then,
we just didn't took care about what is the equilibrium structure of ethylene and what are the really relevant structures. We did it somehow quick and dirty and generated the training set for ethylene and the other molecule.
Okay, and the other question is very quick. This software which you have developed, can it be interfaced with any kind of quantum chemistry source? I mean, if I have some completely different source of getting excited state energies and couplings and so on, is this code flexible, or is this tied to one quantum chemistry machine? So
the code is tied to the molecular dynamics program Schnack, but you can also use it with ASE, for instance, the atomic simulation environment. And and then you can do other molecular dynamics programs too. But it is not tied to a quantum chemistry program, but you need to do your quantum chemical calculations, and then you need to read the them the properties that you need out of your output files and put it into a database that is readable.
Okay, so then it's completely independent, in fact.
Yes,
Oui.
yes.
Okay, thank you very much.
Hello,
You're
no.
welcome.
So Ali, yeah, if you can.
Yeah, my video is blocked, but it's fine.
Is
but-
it by us or?
No, by you, but it's okay. So Julia, thanks for your talk. It's outstanding, really clear. So I have it's a question related to some of the previous questions, which is the nearsightedness of the descriptors that you use. So is there does each descriptor have like a weight, I guess, associated with it? And is the weight of that site interpretable physically? So what I have in mind is the following. So you have a chromophore or fluorophore that's built up from subcomponents, and you want to understand, right? What is the fluorophore? What is the chromophore? And can one interpret the weights in some fashion, also in a time-dependent way?
It's a very, very good question. Thanks a lot. So at the moment, there are 100,000 or so parameters in a network, and I would say it's hard to interpret it. You can do some sensitivity analysis, I think, and propagate back. But there are some methods at the moment that are being developed, especially exactly in this direction. It's explainable artificial intelligence for regression, and there are Shapley values that are used, and I think counterwise layer propagation, which can, I think, also be used for message passing networks. But it is quite complex, as far as I know.
Yeah,
so
I imagine.
Straightforward.
Yeah. Okay, very good. Thank you. Thank you very much.
Okay.
Yeah, okay. I don't know if there are more questions, but I had one. So there is always this question: what is the maximum size of the system that you can actually study with the Schnack method? Take that. How many atoms?
That's a very good question. So we did some high throughput screening of molecules that had up to 150 atoms, but there we approximated excited states with orbital energies and used the correction with machine learning to get to GW accuracy, like quasi-particle energies. So maybe with some sort of delta learning, it might be possible. I don't know of any work for excited states with delta learning so far. Yeah, but otherwise it's limited by the reference method, I would say. Because
so the electronic structure, you mean?
Yes, electronic structure method, yes. And especially because the higher you go, the more states you have. And at some point in materials, when you have a band, you need to describe it differently. It's a lot of questions.
So that's the number of atoms, and how many excited states can you treat reliably?
So depending on how flexible the system is, if it's like tyrosine, maybe 30 to 50 and about 30 states or so.
Okay.
I think. And also it depends if you have singlets and triplets. I think only singlets is much simpler case than adding triplets.
Okay. And one more question. Do you plan to extend the dynamics part to include quantum effects in those ring polymer type of approach? Or?
So Reinhard Maurer, with whom I was at the University of Warwick, so they developed a Julia package for molecular dynamics. There they also have ring polymer dynamics. And I think they also interfaced it with, I think it's already available, interfaced with machine learning, but not for excited states at the moment.
Okay.
But for the ground state.
Well, thank you again. I don't know if there are additional questions.
Thank you
Wow.
a lot for the invitation.
Otherwise, thanks for giving this talk. It was quite interesting, and I hope many people will download the Schnack code and hopefully use it in
Thank
the near
you.
future. Yeah.
Julia, as a
Have a nice
German
day.
speaker, why did you choose Schnack as a as a name? Because it
Right.
makes one really think of sleeping, no?
Yeah, I know,
Yeah.
I know. I think it was Michael who said Schnack. Michael Kastiger. They said they had Schnet, and then we thought Schnet and shark makes Schnack.
Schnack, okay.
Okay. Thank you.
Thank you.
Thank you,
Bye.
everyone. Bye.